Hello and good evening. Welcome to Monday Night Office Hours. Oh, Kate, great question. So what type of orbital does a lone pair have? And the answer to that question depends on a molecule's hybridization. So, for example, if you look at the lone pair on oxygen in a molecule of water, so because oxygen is sp3 hybridized, that means that the lone pairs on oxygen are actually contained. So we know we have sigma bonds between the oxygen and the hydrogens. And the lone pairs are actually contained inside sp3 hybrid orbitals, because those are the types of orbitals on oxygen in this molecule. Hey, Lauren, how's it going? But if, for example, you took, let's look at carbon monoxide. Oh wait, hang on, I want that in black. If you look at carbon monoxide, whose Lewis structure looks like so, and actually has a formal negative on carbon and a formal positive on oxygen, if you look at the hybridization here for either carbon or oxygen, it's sp hybridized, which means that our lone pair here is actually contained inside an sp hybrid orbital. So really, Kate, the answer to your question, what orbital does a lone pair have, depends on the hybridization of the atom that carries it. So it'll be different in each. It'll be unique in each molecule, I guess is what I'm saying. So yeah, that is an excellent question. I am going to pull up my my textbook real quick, so that we can hit up that question you have from chapter 10. Lauren, that is an excellent question. And the answer is yes. It doesn't matter if an atom has multiple bonds; it still counts as one electron group. So it doesn't matter if you're double bonded, if you're triple bonded. When you're counting electron groups, it's just the number of atoms that are attached and the number of lone pairs on that atom. And the reason why a multiple bond still counts as one group is because even though there's a lot of electrons involved, like here with this triple bond, there's 6 electrons, they're all kind of clumped in the same space, so they kind of create one kind of repelling environment. All right, and then Kate, to answer your question, why is carbon sp hybridized? So when you are determining the hybridization, hybridization is a result, as a consequence of what the geometry is around that atom, how many electron groups, and around this carbon we have one atom attached to that carbon, and we have one lone pair, giving us a total of 2 electron groups. And when you have 2 electron groups, that means that you need 2 orbitals, right, to hybridize in order to make that structure. So 2 electron groups always equals sp hybridization. So you have to use one s and one p in your hybridization scheme. Oh, really? Okay, here, hang on. Let me... It's fine in my headphones, but let me... Here, I can make an adjustment. 1, 2, 1, 2, 1, 2. Jason, is that better? Is this better? Now that and I'm like, is that better? And then I'm like quiet because I'm waiting for your answer. I guess I should probably keep talking so you can hear where the sound levels are at. So 1, 2, 1, 2. Does that make sense, Kate? Awesome. You are so totally welcome. See, I'm pulling up my okay, awesome, Jason. And thank you for the feedback too as well. So because my the volume control that I have on my headphones is independent of the gain that's the output audio for the live cast. So so it sounds the same in my headphones, but it's not necessarily reflexive of the audio output to the channel. Okay. So I've almost got... Okay, we need chapter 10, though. That's chapter 9. All right, you needed chapter 10. What was that? Number 62. Oh, are my my numbers up? Heck, yeah, they are. Let's see. Because it is November 30th. Jason, thank you for the heads up. All right, let's see. Still looking for number 62. All right, let's see. Okay, 62. Write a hybridization and bonding scheme for each molecule, and specifically 62D. Write a hybridization and bonding scheme for each molecule. Sketch the molecule, including the overlapping orbitals, and label all bonds using the notation in example 10.6 and 10.7. Okay. So problem D, they want us to do this for boron trifluoride. Now, so first things first, before we can draw kind of the structure showing all the bonding orbitals and all that stuff, overlapping orbitals, we need to know what the Lewis structure of this guy is. So step number 1 is going to be drawing the Lewis structure. And boron has 3 valence electrons. Fluorine has 7, but we have 3 of them. So 3 times 7 is 21. So we have a total of 24 electrons in our budget to spend. Boron is going to be our central atom, mostly because when you look at the Lewis dot structure for fluorine, it has 1 unpaired electron. It likes to make 1 bond. The Lewis dot structure for boron has 3 unpaired electrons. It likes to make 3. So boron is a better candidate for our central atom than fluorine. All right, so first step, we're going to attach all of our fluorines to our central atoms, spending 2, 4, 6 electrons, leaving us with 18. All right, now to complete fluorine's octet, right, it has access to 2 electrons, it needs 6 more, and so we've got 3 fluorines in that predicament. 3 times 6 is 18, and we have 18 electrons in our budget. So we have enough electrons to complete fluorine's octet. All right. Now, we're out of electrons at this point in time. We've spent all the electrons in our budget. Boron still does not have a full octet, but we talked about this in lecture. Boron is the rare exception that is actually, boron's actually okay with having 6 electrons. Boron can break the octet rule and have 6 electrons. So even though the octet rule is super important, boron is just one of those strange, not one of the strange elements, it's like kind of the only one that rolls with less than 8. But it does, and it's fine. So here we have our Lewis structure for BF3. I'm going to draw this on our next slide, and we're going to use this to kind of draw a 3-dimensional, wait, no, not BH3, BF3. Representation of all the orbital overlap, 3-dimensional shape, all that stuff. So here's the Lewis structure that we're going to base our more detailed sketch on. All right, so so we need to determine the hybridization of our central atom boron. And boron has 3 atoms, 0 lone pairs. So we have 3 electron groups. All right, that tells us 3 electron groups means that we have a trigonal planar Vesper geometry, and it also tells us that we are sp2 hybridized. All right, trigonal planar sp2 hybridized. All of our bonds are going to be in the plane of the board, so everything's going to be 120 degrees apart. All right, 120 degrees apart. This would be our three-dimensional representation of the molecule. But they want us to show the overlapping orbitals. All right, so to do that with boron, we've got 3 sp2 hybrid orbitals. Then we have fluorine coming in at each position. And fluorine is going to overlap with boron to make sigma bond, and it's going to do so with each of boron's sp2 hybrid orbitals. All right, and then we're just going to add our lone pairs for completeness sake. So what they're asking for in this problem is kind of like the, those three-dimensional depictions of the bonding orbitals that I was drawing in class. They just want you to do those for all of these, but this would be the three-dimensional sketch. We've already talked about the hybridization for the overlapping orbitals to form the bonds on BF3. Well, so it actually depends upon, it actually depends upon how you draw the Lewis structure. So this would be the three-dimensional representation. It's trigonal planar, so it's flat. If you're drawing, this would be the drawing based off of this Lewis structure, this resonance structure. But there is another resonance structure, and this may be the one that they're basing it off of. So I drew this Lewis structure. And I stopped there because boron is totally allowed to break the octet rule and have fewer. But you could draw another Lewis structure where you take the one of your lone pairs off of fluorine and you use it to make a multiple bond to boron. If you do, there's a couple of consequences. First, it would put a partial positive on fluorine and a partial negative on boron. You'll notice that in this Lewis structure, boron's hybridization is sp2 because it's got 3 atoms attached. But you'll notice that fluorine, as drawn right here, has one atom and two lone pairs attached. That's 3 electron groups. So this would also be sp2 hybridized. Now, should you choose to draw this Lewis structure and then use this Lewis structure for the one that you're going to draw the 3-dimensional kind of orbital picture for, if you base it off of this one, things are going to look slightly different. So again, I'm going to just redraw something right here. Let me just finish putting in all of my lone pairs. All right. So if we're going to draw the 3-dimensional picture here, we still have boron making 3 sigma bonds. To all 3 fluorines. So we still have all 3 sigmas in play. But now in this Lewis structure, you'll notice we've got that double bond, so we need to account. In this Lewis structure, we have a pi bond going on as well between boron and fluorine. So to draw our pi bond, we draw the p orbitals, and because they're engaging in indirect orbital overlap, they blur both above and below the existing sigma bond. We're going to shade in one of our 2 lobes and draw the electrons in the other one because they're easier to see. So if you were to use this resonance structure as the Lewis structure that you're going to base your 3-dimensional representation of all the bonding orbitals, then this is how it would look. Let's not forget, we have a partial positive and a partial negative on boron. Now, if you're wondering, okay, which one is correct? The answer is they both are. They're 2 different resonance structures of the same structure. So the true structure of the molecule is a combination of the 2 of them. And if you're worried about 2 vastly different answers both being correct and wondering, well, which one would show up on an exam, I'm not going to put boron on the exam for this reason. It's a more interesting scenario. But it's complex and it's nuanced to a point on a level that just doesn't fit well with the online testing format. So I wouldn't ever throw something like this on an online exam because it's just it's more nuanced than the form will afford. But either one of the depictions that I drew, this one and the previous one, are correct because the true structure is kind of a hybrid. It's a combination of those 2. Awesome. Oh, Lauren, did I miss it? Let me see. Oh, no. Kate, I actually already answered it, but if you missed it and were wondering, for electron groups, it's just the number of atoms plus the number of lone pairs. So a triple bond doesn't count as 3 electron groups; it just counts as 1, because even though there's multiple bonds, all those electrons are kind of huddled around the same space. Oh, no, Kate, no reason to apologize. None at all. Okay, and yes, I can totally go over the molecular geometry of NCl2 plus. I don't happen to know the name of that specific polyatomic ion off the top of my head. But I can definitely talk about the geometry. All right, so to figure out the geometry first, we need to draw a Lewis structure. And to do that, we need to start by counting our electrons. So nitrogen has 5 valence electrons. Chlorine has 7. But because we have 2 of them, that means chlorine is bringing 14 valence electrons. And now we have this positive charge, which means that we have 1 fewer electron than we should. So we have to subtract 1 from our total count. So instead of having 19 electrons, we will have 18 electrons to spend to build this structure. So I'm going to put nitrogen in the center. And spend 2 4 electrons. Let's see, so minus 4. In order to attach my chlorines, leaving me with 14. Now, each chlorine needs 6 more electrons. We've got 2 of them. So I'm going to spend 12 electrons in order to complete chlorine's octets. All right, so completing chlorine's octets. Now we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right, now we only have 2 electrons left in our budget, so we're going to give those to nitrogen. But we still have some stuff to figure out here because nitrogen as drawn only has 6 electrons. We know we need to have 8, so we got to take a lone pair off of one of our chlorines and use that to make a multiple bond. And our formal charge of positive 1 will rest on this chlorine. So that is the Lewis structure for NCl2+. All right. Now, the question is, what is the geometry here? What is the geometry? So to determine our geometry, we first need to look at how many groups do we have around our central atom. All right, so let's investigate. So nitrogen has, here we have 2 atoms attached and 1 lone pair on our central atom, right? 1 lone pair. We're not counting total central atoms, just central atoms on, just lone pairs on the central atom. So we have 3 electron groups, which means the electronic geometry is trigonal planar. But as we know, when you have a lone pair, things change, all right? So for the electronic geometry, every trigonal planar molecule is the same. We got bond angles of 120, spread everything out. Everything's in the same plane. Oops. But when we try to figure out our molecular geometry, we're not looking at the shape that all the electron groups make. We're just looking at the shape that the atoms make. And so the molecular geometry here will be bent, because it kind of looks like a bent line. Kate, great question. Awesome. Okay. Here, let's take a look at ICL4. Leanna, great question. So if you look at it, the hybridization here, oops. We have 3 electron groups, the hybridization is going to be sp2. So to determine hybridization, you always look at the number of electron groups, and for each electron group, it takes one orbital. So since we have 3 electron groups around our central atom, we're going to use 3 orbitals in the hybridization, which is why it's sp2. We use 1s and 2 p orbitals. Alrighty, let's take a look at yet another polyatomic ion that I don't know the name of. ICl4. So, iodine has 7 valence electrons. Chlorine also has 7, but we have 4 in play, so it's going to bring 28. And then we have our negative charge, which tells us that we have 1 additional electron in this molecule. So this will leave us with 36 electrons in our budget. We're going to throw iodine in the center. And we'll begin by attaching all of our chlorine, spending 2, 4, 6, 8 electrons, leaving us with 28. Next, we need to complete chlorine's octet. Each chlorine requires 6. We have 4 of them. 6 times 4 is 24. We have enough electrons in the budget to satisfy chlorine. So it'll leave us with 4 electrons left. All right, so we have, let's draw all these in. It'll take just a second. All right, there's all our chlorines with full octets. But now you'll notice that we have 4 electrons left. We have 4 electrons left, and so we got to place them on our molecule. Fortunately for us, we have multiple atoms that are allowed to break the octet rule. So we theoretically could give them to iodine or any one of these chlorines. It's actually only correct to give it to iodine, however, and I'll show you why in just a second. But first, let me add these in. So this is the correct structure of the molecule. In this structure, iodine bears a charge, a formal charge of -1, and so this is the correct Lewis structure. But I want to take a moment to show you why it's why we want to give all the lone pairs to iodine and not spread them to our chlorines. All right, so I'm gonna open up a new slide where we're gonna look at and evaluate a couple of the different options and hopefully understand why giving both lone pairs to our central iodine is the best option for our 2 extra lone pairs. All right, so putting them both on iodine here is one option. But there are a couple others, so let's kind of consider them, evaluate them, and look at the difference. So for the first one, we have a formal negative charge on iodine. If you look at there's really only 2 other options if you consider them. Yep, Kate, you got it. It comes down to minimizing our formal charges. It totally does, and you'll see in graphic detail once we place these lone pairs elsewhere. So if we put one on iodine, and let's say we give another one to one of our chlorines, in this structure, chlorine. So iodine would have a charge of +1. And chlorine would have a charge of -2. All right, and then the last option is what if we give iodine none of the lone pairs, and we put the rest on chlorine. If we do that, then iodine would have a charge of +3, and then each chlorine would have a charge of -2. So the reason why, oh, I see what you're saying. Why don't you do multiple bonds between, like the chlorine with the -2 and the iodine, for example, to minimize formal charge? Kate, that is a great question. And as it turns out, chlorine and iodine, actually I should say chlorine, bromine, and iodine are all really bad at forming double bonds. I should say multiple bonds. They tend to be very weak and are rarely seen in nature. So even though it's theoretically possible, the best Lewis structure is going to be this guy, because we don't have any iodine or chlorine multiple bonds, and it has minimal formal charge. Totally. I can tell. I think this is the second time it's come up in an office hour, which is a really interesting molecule. It's a really interesting problem. So I'm glad you've been thinking about it and asking about it. Sure. Here, let me pull that problem up. Yes, Leanne, I totally can. All right, let me just do this one first. So determine the electron geometry, molecular geometry, idealized bond angles for each molecule. In which case do you expect deviations from the idealized bond angle. Okay. So so Kate, what they're talking about there when they talk about deviations is so for example, if you compared methane, the methane bond angle to the bond angle in ammonia. All right. Now, both of these have tetrahedral electronic geometries. So with methane, we have bond angles of 109 degrees. Actually, okay. Yes. Okay. Yes. Correct. Sorry. Yes. ICl4 with a -1 charge has 6 electron groups total. So Kate, when comparing methane to ammonia, they both have tetrahedral electronic geometries, but because of this lone pair, it squeezes the bond angle down by 2 degrees because that lone pair has more repulsion than a bond. And this is what they're talking about when they talk about deviations in this problem, because the bond angle for ammonia deviates from the tetrahedral bond angle of 109 degrees, it deviates from it by 2 degrees. So that's what they're talking about there with the deviations. Totally. So when we, Kate, you are so totally welcome. So when we look at these problems, so for example, 36A is CF4. All right, when you look at the Lewis structure here, for CF4, it looked like this. Now I've got all these dots to draw. All right, so that is, so that's the Lewis structure. Now for this one, for a central atom, we have 4 atoms, 0 lone pairs, so 4 electron groups around our central. So we would expect a tetrahedral. So for electronic geometry, it's tetrahedral. Our molecular geometry is the same, because we have no lone pairs, and 0 lone pairs means that there's no deviation, that our bond angle is 109 degrees. All right, I think that's all the stuff they asked for. Yeah, whereas if you compared this to, so that was part A, if you compare this to, let's say part C, where we have the molecule OF2, if you draw the Lewis structure here, it would look like so. Right? Yep. And so for our central atom, oxygen, we have 2 atoms attached, 2 lone pairs, so 4 electron groups, which means our electronic geometry is tetrahedral. But our molecular geometry is going to be different because we have 2 lone pairs. So our molecular geometry will be bent. And we do, because we have 2 lone pairs, we'll expect a deviation from the we will expect to have a deviation from the ideal bond angles of 109. We've got 2 lone pairs, so it's going to pinch it down to 105 degrees. All right. So that is how you tackle. Oh, I'm so glad. Oh, let me see. I have... Oh, Kate, you are so totally welcome. I will totally check my email. I think we have another Lewis structure question on the stack. So let me hit this up and any other live questions, and then when things get a lull, I'll go back through my email. I haven't had a chance to open it up. So so it's probably in there, but I haven't had a chance to look for it. Okay. Let's see. Okay, Leanna, thank you for being patient. Let's go ahead and do take a look at thiocyanate. Oh, weird. Jason, the answer to that question is it should become available at 12 like normal. There shouldn't be a reason. Oops, so let me log in and take a look. If it's not, I will correct it. That's weird. I have no idea why it's set for 3 p.m., but I will change that now. Oh, and for some reason it was set to 60 points, not 70. Okay. And Lauren, yes, one single electron does count as one electron group. And so just as always with hybridization, count up the number of electron groups, and that tells you how many orbitals should be included in your hybridization scheme. All right, Leanna, thank you for being patient. Let's actually get down to business and deal with this thiocyanate situation. So sulfur brings 6 valence electrons. Carbon brings 4. Nitrogen brings 5. And our negative charge tells us that there's 1 extra electron in this molecule. So we have 16 total valence electrons to spend. I'm going to... Lauren, you are so totally welcome. I'm going to spend, let's see, 4 connecting both sulfur and nitrogen to our central atom. So that leaves us with 12. All right, and now we can complete Sulfur's octet if we spend 6 electrons. Leaving us with 6. And we can complete Nitrogen's octet if we spend our remaining 6 electrons. Oops. All right, leaving us with 0. Now, the problem here is that carbon doesn't have a full octet, and so we need to use some of our lone pairs and turn them into double bonds to complete carbon's octet. So this is a Lewis structure for the molecule thiocyanate. That's SCN with a negative charge. It by no means is the only one. There definitely are resonance structures that you can draw. For example, you could do a double bond between sulfur and carbon. And then a double bond between carbon and nitrogen. And in this Lewis structure, nitrogen would have the negative charge. And these two are these are resonance structures of each other. Either one is totally acceptable as an answer because they both have minimal formal charge and complete octets for every atom in the molecule. So if you look at the central atom, which I'm assuming that's the one you're asking about, in either Lewis structure, either resonance structure, there are 2 atoms. Zero lone pairs. So together, they're 2 electron groups. And 2 electron groups means that you need to use 2 orbitals for the hybridization. So it'll be sp. Totally. Here, let me pull those up. Of course. All right. Let's see, number 64. Write a hybridization and bonding scheme for each molecular ion. Sketch the structure, including overlapping orbitals, and label all bonds. Excuse me. Okay. So, let's see, 62A. Oh! Oh, sorry, you asked this earlier and I totally forgot about it. So, for 62A, yes, sorry, in 62A, doesn't matter where the bromines land relative to the hydrogens, because every position on a tetrahedron is equivalent. All right, so let's take a look. Okay, so we're doing 64. Starting with A. So we're looking at COCl2. All right, now, and they tell us that carbon is the central atom, which is nice of them. When you, so I'm just going to go ahead and dive in and draw the Lewis structure for this compound, because we need the Lewis structure to determine hybridization and all the rest. All right. So when it comes to the hybridization for carbon, carbon has 3 atoms, 0 lone pairs, which means we have 3 electron groups. That means our shape, our Vesper geometry, is trigonal planar. And because we have 3 electron groups, that means that our hybridization uses 3 orbitals, sp2. All right. Now, if we're going to draw that out, we have a sigma bond between carbon and oxygen. We also have two sigmas between carbon and chlorine. Right, two sigma bonds there and there as well. Finally, between carbon and oxygen, we have one sigma, but we also have that second bond, right, which is going to be a pi bond. To draw that pi bond, we start by drawing our two p orbitals, blur them together through indirect orbital overlap. Go back, touch things up a little bit. We know we have to shade one of our two lobes. All right, so there we have the bonding orbitals for COCl2. So if we're going to label our bonds, we have a pi bond here, right? Two lobes. And then we have three sigmas. One there, one here, and one there. We've already taken care of our hybridization. So we're good to go there. It's part A. Part B, we are doing BRF5. The Lewis structure here in the Lewis structure, bromine has a lone pair and then 5 bonds to fluorine. Not to 1 fluorine, but to 5 fluorines. And it always takes a while to draw all the lone pairs. Now, our hybridization here, let's take a look. We've got 5 atoms, 1 lone pair. So that's 6 electron groups. Which means that 6 groups means that we have a sp3d2 hybridization. It also means that we are, square pyramidal. Now, it's an octahedral electronic geometry, and there are 2 ways to draw octahedra. You can draw 4 things in the plane, 1 wedge and 1 dash. But because one of these things is a lone pair, we don't have to draw that in. And I think this is going to be the easiest structure to base the 3-dimensional representation of the bonds off of. All right, so when we draw this, oh, sorry, that's Br. It's bromine. So we've got 5 sigma bonds to draw. I'm drawing the 4 that are in plane first because, well, frankly, because I think they're going to be the easiest to draw. And then that 5th one is going to come wedged out. So it's kind of out in front. So we got 2 there, 2 back behind, 2 up here, 2 in there, 2 in there, and then we have all of our lone pairs. There we go. So that would be, oh, and let's not forget, bromine still has a lone pair. So that would be BRF5, which was part B. A, B, C is next. With XEF2. All right, so this loose structure looks like so. And xenon has 3 lone pairs around it, yes. So, looking at xenon, we have 2 atoms attached, 3 lone pairs. That's 5 electron groups. Which means that we are dealing with an sp3d hybridized molecule, which is a trigonal bipyramid. Now, a trigonal bipyramid looks like so. You've got the 3 equatorial positions and the 2 axial positions. But fortunately for us, the electrons all occupy the equatorial positions, which means this is going to be fairly straightforward to draw. Because we just have 2 sigma bonds between xenon and fluorine. So, really, oops. it's just going to look like so. We'll have 3 sets of lone pairs around our central atom and 3 sets of lone pairs around each fluorine. So that is the sketch that they are looking for part C. I3 minus is going to be is going to look somewhat familiar. So if we look at ABCD part D, we're doing I3 minus. If you draw the Lewis structure, you have iodine in the center with 2 iodines attached. And the iodine in the center actually has 3 lone pairs. So this is the exact same situation that we had with xenon, sp3 dehybridization. It's going to be the exact same picture, just with iodines instead of xenon and fluorines. Whoa. There it is. All right, so that was 64. Let's take a look at 66. Write a hybridization and bonding scheme for each molecule that contains more than one interior atom. Indicate the hybridization about each interior atom. Sketch the structure. All right. Okay, so here this is 66. We'll start with part A. In part A, we're looking at C2H2, which, when you draw the Lewis structure, the Lewis structure looks like this. All right, so here we have, they want us to label the hybridization for each interior atom. And this carbon has 2 atoms, no lone pairs, so it will have a hybridization of sp. Same with the other carbon, right? We have 2 atoms, no lone pairs, so whenever you have 2 electron groups, you need to use 2 orbitals for your hybridization. So it comes out to be sp hybridized. Now, taking the atom, the carbon on the very left is forming a sigma bond with hydrogen. It is also forming a sigma bond with the carbon on the right. The carbon on the right also forms a sigma with its respective hydrogen. And those are all our sigmas. Now we have to account for the triple bonds, right? And as we saw in class, this means that we have 2 pi bonds. The first we're going to form using PZ and the magic of indirect orbital overlap. So we shade one of our two lobes. Throw 2 electrons up in there, and we're good. Now we have to make the second pi bond. This is with, we form this pi bond using px, and it comes out of the board or screen at us, and then back into the screen away from us. So it comes out in front, and then goes back behind. I'm just going to clean it up. There we go. So that's out in front, just very clearly. I'm going to shade the back. And I'm going to throw a couple of electrons in that lobe out in front, and that is a 3-dimensional picture of the bonding orbitals of in acetylene C2H2. We've labeled the hybridization. We've shown the structure, including the overlapping orbitals. Let's label all bonds. We haven't done that yet. So we actually have a couple of pi bonds. Here's our first pi bond. That's pi. Our second pi bond, these two lobes here. So we've got 2 pi bonds. And then sigmas, we have here, here, and here. All right. All right. Let's do part B. Part B, we got to look at C2H4. Now, when you draw the Lewis structure, comes out like this. If you look at the hybridization, this carbon has 3 electron groups, which means it will be sp2 hybridized, same with that carbon. So we're dealing with sp2 hybridization for both. Now, I actually think it's easier to see the bonding orbitals if we draw the molecule in this orientation. So the carbon-hydrogen sigmas are in plane, but the plane that is perpendicular to the screen. I just think this is the easiest way to see them, so that's how I'm going to draw it. First, let's get our carbon-carbon sigma going. Next we have our carbon-carbon pi. Now let's clean up the structure just a little bit. We're going to shade one of our 2 lobes. Place our electrons. Now, We've got 2 wedged sigmas. Kind of 2 dashed sigmas. May not be the prettiest picture that I've ever drawn, but it'll get the job done. And these sigmas are all between carbon and hydrogen. All right, now let's label our bonds. We have the 2 lobes of our pi bond, and then we have our 5 sigmas. All right, so that is C2H4. Moving to part C. We have the skeletal structure. Okay, so we have C2H6. All right, now when you so let's draw our Lewis structure here. Now, when you look at the hybridization, whoops. Sorry. Okay, there we go. Photoshop's back. When you look at the hybridization of each carbon, they have 4 atoms attached, which means that each carbon is sp3 hybridized. All right. So let's think about how to draw this thing. Well, every 4 electron groups is tetrahedral electronic geometry. Each tetrahedron has 2 bonds in the plane, followed by 1 wedge and 1 dash, so that's the first carbon. The second carbon also has 2 bonds in the plane, followed by 1 wedge and 1 dash, so that is the second carbon. So this is kind of the shape that the molecule takes. That's the shape the molecule takes. Let's go ahead and draw the overlapping orbitals showing all the bonds. So we have our carbon-carbon sigma. We're going to have now a lot of carbon-hydrogen sigmas. Those are all the ones that are in the plane. Now we need a sort of wedged sigma. Followed by a dashed. Then the same over here. So that would be C2H6, and all these bonds are sigma bonds. All 7 of them. All right, and that is number 66. Now, let's take a look at 68. So consider the structure of the amino acid, aspartic acid. Indicate, the hybridization about each interior atom. All right, I'm going to, and then they give us a structure here. I'm going to redraw it as a Lewis structure. Because they tell us the atoms. And they ask us to label the hybridization. So this will just take a minute to draw. But now here we are. All right, and now here's the thing. Again, for labeling hybridization, what you got to remember is the number of electron groups. I'm so sorry. The number of electron groups determine the hybridization. So 2 groups is sp, 3 groups is sp2, 4 groups is sp3, 5 groups is sp3d, and 6 groups is sp3d2. All right. The number of electron groups around an atom determines the number of orbitals that are used in its hybridization scheme. So when you look, for example, at this oxygen has 2 atoms attached and 2 lone pairs. So those are 4 electron groups, which means it's sp3 hybridized. When you look at this carbon has 3 atoms and 0 lone pairs, so that's 3 electron groups, so it is sp2. When you look at this oxygen, it has 1 atom and 2 lone pairs. 3 electron groups makes it sp2. When you look at this carbon, 4 atoms attached, 4 electron groups, sp3. This nitrogen, 3 atoms plus 1 lone pair is 4 electron groups, sp3 hybridized. This carbon, 4 atoms attached, sp3. This oxygen, 2 lone pairs, 1 atom, 3 groups, sp2. Whoa, sp2. This carbon, 3 atoms, no lone pairs, sp2. Finally, this oxygen, um, 2 atoms, 2 lone pairs, 4 groups, sp3. So that is how you handle hybridization. You just look at the number of electron groups around the atom, and that takes care of it. Ah, Leanna, I totally can. All right, let's talk about the electron domain and hybridization for the azide ion. All right, so so there are a couple of resonance structures we can draw for the azide ion that are equivalent. You could draw it like so. Actually, this one's probably the best one. So you've got a formal positive in the center, and then two formal negatives out on the ends. So let's talk about electron domains and hybridization. So when it comes to the electron domains, or I call them electron groups, we look at our central atom, and on our central atom we have two atoms attached and no lone pairs, again directly on the central atom. So we have two electron domains or electron groups, and so whenever you have two electron groups, that means your hybridization is going to be sp. So it is sp hybridized. Oh, totally. Well done on doing it right, Leanna. It's totally natural for doubts or second guessing to creep on in. But the best thing to do is to go with your gut when you're in doubt. What up, dude? How you doing? Dude, I feel ya. Alrighty, and that brings us to 10 o'clock, so I'm going to go ahead and close down office hours. Thanks everybody for coming out, for asking questions. It was a good time. I will catch you all on Monday. No, well, yes, but first Wednesday. Later.